So, welcome back. In the previous class I was talking about the parameter estimation problem, and what we have seen that using super twisting like algorithm it is possible to show that one can able to estimate unknown estimate, and once unknown state is estimated then unknown parameter also can estimated using some kind of algorithm, and we have developed the nature of algorithm, their convergence result, and after that we have also discussed one of the application. In this lecture we are going to extend the super twisting algorithm for multi input multi output case. Okay. So, one of the very active area of research is multi agent systems. So far I haven't taken example of multi agent systems, but in this lecture I am going to talk about the multi agent systems and how basically one can able to implement sliding mode control for the multi agent systems. So in this lecture I am going to first develop the multi input multi output variant of super twisting algorithm, and I am also going to maintain continuity of the control. Why? Because most of time we have multiple robots and somehow that is nothing but some kind of electromechanical system, and it is possible to show that continuous control is more suitable for that classes of system. Okay, obviously we have several other way to implement multi-agent system. Suppose that if we have multiple converters and if I want to control some kind of current and voltage, similarly if I have multiple energy generation source and we want to control the voltage, so we have several different problem that is actually occur whenever we are talking about the multi-agent systems. So let us see how to formulate multi-agent problems, and after that how to apply the sliding mode control for that particular classes of problem. So purpose of discussion, one of the main goal is the formation control. What is meaning of formation control? Suppose that if I have multiple agent, so and out of that agent it might possible someone is leader and all other are the followers. So most of time we have to create some kind of geometrical structure with respect to the or some kind of geometrical shape with respect to the leader. So that class of problem is called the formation problem or formation control problem, because in order to achieve formation I am going to design the control. Meaning of multi-agent means I have multiple physical or some kind of virtual systems. So suppose that if we are talking about computer programs, so it might possible I have several sub program that is running together to satisfy some kind of common objective. So due to that reason multi-agent can be virtual as well as the some kind of physical like robots, like energy systems or several other applications. Here I am going to specify the dynamics of these multi-agent system by double integrator dynamics. It means that I am talking about that whatever system I am going to consider, that is actually defined using some kind of chain of integrator form. Second order chain of integrator form means x1 dot equal to x2 and x2 dot equal to u. Obviously every system has some kind of disturbance, so I am also going to assume that there exists some kind of disturbance, but I am assuming that disturbance is going to enter through the control channel only. But one can able to generalize this concept for any order chain of integrator. Okay. So depending on the problem, obviously complexity of problem become very high, because overall system is now become multi input multi output system. Okay. After that another class of problem is called consensus problem. It means that somehow we are trying to converge to some kind of average of the all state, or sometimes some kind of goal is given and all agent are going to converge to that goal that can represented in terms of the position or velocity. Okay. So both problem I am going to discuss here, and that class of problem we are giving some special name that is called zero formation control problem. Okay, because finally all agent is going to meet at some specific point. Okay. So now during the solution of this problem, I am going to ensure that whatever the formation control or consensus control or whatever target I am going to decide, that I am going to finish within finite time, and due to that reason we need some kind of robust finite time control algorithm. And since I have some kind of time varying disturbance, and due to that reason whatever feedback I am going to define, that is non-smooth in nature. And how to achieve this? It is possible to show that using classical sliding mode control. Since you have second order dynamics and here multi input multi output systems, so what you can do? You can define sliding surface, and after that you can apply the philosophy of multi input multi output classical sliding mode control based on unit vector control, and then also you can able to achieve the same objective, but you cannot able to guarantee the finite time stability if you have second order integrator chain of dynamics. But suppose that if every agent is represented by just a single integrator, then at that time using first order sliding mode control you can able to give guarantee. Okay. So in this class I am not going to discuss about the when I have first order dynamics and then you can apply simple sliding mode control, or second order dynamics and you can design sliding mode control. Our main objective, how to apply higher order sliding mode control theory for multi input multi output classes of system, and due to that reason I am going to first extend the super twisting control in such a way that is applicable for the multi input multi output system. And obviously finite time convergence is guaranteed, and one can also able to prevent the chattering because whatever control I am going to propose, that is continuous in nature, and obviously robustness comes into picture. So whenever we are talking about the class of problem that is called multi-agent problem, so this is fusion of two different classes of problem. Okay. So mathematically, in order to represent this problem, I need the concept of graph theory as well as the control system. So what is role of control system? Control system is somehow whenever all agents are apart from each other, so they are going to actually push all agents such that they will come in some kind of a specific objective. Okay. So how basically one can able to decide that kind of objective of formation? So that is basically given by the graph theory, and once we will achieve that formation, then graph theory is going to maintain that kind of formation with some kind of algebraic or geometrical concept. So I am going to discuss here some part of graph theory. If you are not aware about the graph theory, you can just go through any standard mathematics book, you can easily able to understand. Okay. So what basically I am going to do, whenever I am talking about graph, so graph contain two parts. One part is called the node and another part is called the edge. So suppose that if I have three agent, so three agent means this is one node, this is another node, and this is third node, and this is connection. So this is called edge. Okay. So I have generalized this theory for n node, and obviously in this particular lecture I am going to limit the number of agent, because based on that agent I have to formulate the Laplacian matrix and everything. What is our assumption? It is possible to show that all agents are not directly connected. Okay, and due to that reason it might possible I am not assuming that I have edge with every agent. Okay, it might possible that this and this agent is not connected, but obviously this agent is connected through this agent. Okay, and due to that reason this symbol comes into picture. So now one more important point, it might possible whatever a communication is going to occur between two agents, it might possible that is not bidirectional. Now in order to maintain the formation, one of the requirement is there, and mathematically that requirement is called requirement of a spanning tree. What is meaning of a spanning tree? So we are assuming that somehow all nodes are connected in some way. So and mathematical definition is a directed graph G has directed a spanning tree if and only if there exists at least one root node which direct path to all other node. Okay, so this kind of things we are going to maintain in order to solve the formation control problem, and it is equivalently that globally one can able to reach to any node. Now another algebraic concept, that is called Laplacian matrix. Okay, so during the graph theoretical formulation, automatically this matrix comes into picture due to the communication between the agent, and it is possible to show that this matrix L has always greater than equal to 1 zero eigenvalue, and this is very important, because using zero eigenvalue we are going to prove the two things, that is consensus as well as the formation. And obviously all non-zero eigenvalue that should lie in open right half plane, that we have to ensure. Okay, and if exactly 1 zero eigenvalue, this implies G has directed spanning tree, and I have already assumed that in our case we have directed spanning tree, and due to that reason we are assuming that exactly one eigenvalue we have, and rank of the Laplacian matrix, that is n, it means that L has simple zero eigenvalue. So proof of this particular theorem is given in this book, so please check. Okay, and after that, why these two things are required? So we are talking about the spanning tree. So physically a spanning tree ensures the connectivity in network and gives the feasibility of consensus and formation control. And obviously Laplacian structure, that is talking about the convergence and stability of collective behavior. So our goal to somehow come on some specific formation, and after that we have to maintain that formation. So using this Laplacian, it is possible to show that one can able to maintain the formation, and how to get that formation, that is the role of the control system. So in this particular lecture I am going to assume I have 4 followers, so that is represented by 1, 2, 3, 4, and 0 is going to represent by the dynamics of the leader. Okay, and whatever topology I have considered, that is a spanning tree, it is always possible to show that in some way every agent is connected with this particular leader, and due to that reason one can able to show that here this satisfies the property of a spanning tree. Now I am assuming that whatever dynamics of leader, that is given by this, and here assumption is U0 is not known to us. It means that what control actually one can apply to leader, that is not known to us, but obviously I am assuming that the whatever control here, that control and their derivative is bounded, and this is the dynamics of the follower. So I means, since if you put I equal to 1, then that will represent the first dynamics of first agent, and similarly if you substitute I equal to 2, then second agent. I am assuming that here that agent dynamics is going to contains some part of the uncertainty, and obviously this uncertainty is bounded. In this particular formulation, it is possible to show that only this assumption is enough, but several times it is possible to show that only relative position information is available. At that time it is possible to show one can able to design super twisting kind of observer. Obviously whatever super twisting observer we are going to design, that super twisting observer can be inspired from multi input multi output case, and that is actually given by one of the active researcher, that is Edward. So if you go through the Edward paper, then you can able to see that how to generalize multi input multi output super twisting. Obviously that multi input multi output super twisting here, that is not directly applicable if you have second order dynamics, because we know that super twisting is only applicable for relative degree 1 system, and due to that reason we should generalize this super twisting for somehow second order or second order kind of multi input multi output system. But as a observer you can able to apply whatever super twisting algorithm that is proposed by the Edward. Okay, so if you are assuming just if you have position information, then this assumption is also required. But if you know you have both relative position information, what is meaning of relative information? So here suppose that if I am assuming that 1 is going to communicate with 2, then I have some kind of relative position information between 1 and 2. Okay. 4 is directly connected with 0, it means that I have relative position information between leader and as well as the follower. Similarly, I have information of relative velocity. Now, what I am going to do, since I am going to ensure that after finite time all follower is going to maintain some kind of a specific formation. Okay, it means that some kind of geometrical structure or some kind of geometrical distance that is going to maintain with respect to the leader dynamics. So, this will represent whenever I will put 0, it means that is the position of leader. So, I am going to maintain a specific distance and this delta is some kind of matrix. So, I have to provide what kind of relative distance I want to maintain with respect to leader. Okay. And after that I am assuming that velocity wise both are the equal, one is nothing but some kind of identity matrix. Okay. So, or this is just a, you can assume this as a unity matrix, not identity matrix. Okay. Now, rho I is the effect of follower dynamics and I am assuming that U0, that is nothing but the control to the leader, that is also bounded and their derivative is also bounded, and I have to achieve this kind of convergence in finite time. So, what is key inside? So, full position knowledge is not required, only relative knowledge is required. It means that there is no need to know where that is position of this, position of this, position of this, just relative information is okay for the development of the algorithm. Okay. And what is sufficient condition? Directed path from the leader to each follower, that is not required. Okay. Some kind of way leader can connect to the follower. You can see that this leader is not directly connected to 2, but if there exists some kind of path, so leader can first check the information with 4 can communicate with 1 can communicate with 2. So, direct information of 0 and 2 is not available, but still I can able to achieve the formation. So, just sufficient condition is direct path from the leader to follower we needed, and if that is the case, that is called the spanning tree. So, that we are already assumed. One of the very important thing that comes into picture during this formulation of the problem, multi-agent problem, that is called adjacency matrix. So, how to define adjacency matrix? So, Aij equal to 1, it means that element of the adjacency matrix equal to 1 if agent j receive information from the I, and Bi equal to Ai01 if I receive direct information from the leader, otherwise 0. So, in this way I can able to form some kind of adjacency matrix. In next slide I am going to show you how to form the adjacency matrix. Now, what I am going to do, based on relative information I am going to define the relative position error. So, here Bi, and Bi is nothing but the term where leader relative error means x1i and here x10. So, with respect to leader, now I am going to calculate the actually relative position between the other followers, and similarly this will represent somehow, if you see carefully, then this is the distance between two followers, because several agent we have seen in this figure that is not correct directly connected to the leader. Okay. So, at that time again error dynamics that comes into picture, because finally what is our goal? Our goal to push all agent towards the specific formation, and due to that reason some exchange of information is required. Okay. And delta 1i is nothing but some kind of offset formation, offset term, because that we have to maintain, that is our goal, that we have to maintain this much of the offset with respect to the leader. Okay. And after that we can able to define the relative velocity. So, whenever we are defining relative velocity, obviously we are going to take the derivative of this, and automatically when we will take derivative, then if this is delta means relative offset is constant, then that become 0, and due to that reason there is no offset term that is going to appear in the velocity. Now I have already told you that one of the very important thing that is the adjacency matrix. Okay, so adjacency matrix is actually defined by this particular algorithm. So we have already seen that Aij equal to 1 if agent J receive information from I, 0 otherwise. So based on that, basically we have created this kind of matrix. Okay, so 0 will get information from same, and due to that reason that become 0. So due to that reason in this row everywhere you can able to see 0. Okay, and after that now I have to formulate this matrix D, because using help of this matrix and adjacency matrix one can able to formulate the Laplacian matrix, and Laplacian matrix is very important to maintain stability as well as the formation. Okay, so how basically one can able to substitute the diagonal of D0, D1 and Dn. So for that what we have to do, you can see here that Di, so I equal to 0 if I substitute, then A0 comes into picture, and I have to, after that I have to vary J from 0 to n, and after that I have to take the summation. So in this way I can able to calculate the Di each element, and after that we can able to define the Laplacian matrix. Okay, and after that similarly I can able to define the adjacency matrix just for the follower, that is the subgraph. Subgraph is nothing but the subset of the graph. Okay, so in this way I can easily able to formulate the formulation of the Laplacian. Okay, and Bi is nothing but if agent I is connected to the leader, otherwise 0. In this way basically I am going to define the B bar matrix. Okay, and it is possible to show that is nothing but the diagonal of A10, An0. So full Laplacian matrix one can able to construct based on this, because now I have information of each and everything. So every information I am going to keep inside this matrix, and then I can easily able to formulate the Laplacian matrix. Now you can see here that I have defined the formation error. So now I am going to stack the all formation error inside some vector that I have defined phi1, and velocity I am going to actually stack into phi2. So what is our objective? I have to maintain phi1 and phi2 equal to 0. So once phi1 and phi2 equal to 0, then it is possible to show that all agent is going to maintain some kind of a specific formation with respect to the leader, that I am going to establish in the last. So but our first goal, using design of some kind of continuous control, I have to maintain phi1 and phi2 equal to 0. So next subsequent slides I am going to first prove this, that how basically phi1 and phi2 equal to 0. This is not very easy task. Okay, so what I am going to do, first I am going to represent everything in multi input multi output second order chain of integrator. Why multi input multi output? Because each agent has some kind of control input. Similarly leader also has some kind of control input. So if you substitute everything, it is possible to show that this kind of structure automatically comes into picture. Okay, where L bar I have already defined, L bar is nothing but the Laplacian of follower dynamics. Okay, so simply you can easily able to check that this kind of dynamics comes into picture. Now Laplacian matrix for the follower, whatever graph I have taken here, because just in order to ensure that whatever theory I am going to develop, so this kind of a spanning tree I have taken, but you are free to select any kind of a spanning tree. So for that I am going to actually define the adjacency matrix as well as D matrix, and then I am going to define the Laplacian. Okay, so that kind of things basically I am going to do here, and in this way numerically you can able to check that how basically one can formulate the Laplacian matrix and B bar. Okay, now control objective we have already seen that U I have to design such that this will ensure infinite time, and control I have to maintain continuous, and I am just assuming that whatever leader control that is bounded. So basically control structure, if you see carefully, it is possible to show that whatever Laplacian matrix of subgraph of the follower that is invertible. Okay, it is not difficult to prove by construction. So basically this is invertible. Now I have two parts, U0 that is nominal part and UD that is the disturbance rejection part. Okay. So if you see any super twisting algorithm, first order super twisting algorithm, if you see carefully, so if you take this kind of a structure, just this kind of a structure, it is possible to show that in absence of any disturbance, x1 tending towards 0 as t tending towards some finite value t. Okay. So now suppose that if I have system like x1 dot equal to u plus d, now how to compensate this disturbance d? So using this control, it is not possible to completely compensate this disturbance, because at x1 equal to 0, control term equal to 0, because u I have proposed like this. Okay. So now our aim is to add some extra term. So how to add extra term? So due to that reason, in super twisting, construction of super twisting, what Professor Levante has done, actually they know that this controller is finite time stable. So based on the homogeneity, they have added one more term, that is x2 dot equal to minus k2 signum x1. Okay. So this term is basically responsible for the compensation of these kind of disturbance. So exactly same principle I am going to generalize the super twisting algorithm. So this super twisting algorithm contain two terms. First term is exactly same, like you can see this kind of a structure. So obviously I have second order integrator, and due to that reason, here I cannot able to write phi 1 by somehow mod phi 1. So I have to give some specific weight. So I have given weight equal to 2 by 3. It means that phi 1 homogeneity degree of phi 1 is lambda power cube. Okay. And here homogeneity degree of the phi 2, that is basically nothing but I have to maintain lambda square, and in this way I can able to make whole controller that is homogeneous in nature. Okay. So this is actually based why I have selected this kind of weight, that is the philosophy of that. And after that discontinuous term, you can see that I have constructed like this, and this p dot I have defined like u0. And what is u0? u0 I have proposed like this. Okay. So now what is theorem is telling us, that if you have this kind of dynamics, I have coupled everything with help of the graph theory, and after that we are going to show that if rho is represented by this, so this whole term I am considering as a disturbance, because u0 I don't know, rho I don't know. Okay. So it is possible to show that if you design this set of gain, then phi 1 and phi 2 both equal to 0 in finite time. Okay. Proving of this is not so easy. You have to develop Lyapunov function, and it is possible to show that developing of some Lyapunov function v, and that is function of some set omega 0. I will define what is meaning of this set, and it is possible to show that there exists two positive symmetric definite matrix, and here lambda max and lambda mean is the eigenvalue of this matrix, positive symmetric definite matrix. Then within this time I can able to converge to the equilibrium point. Okay. So what I have done, I have substituted the control, and after substituted the control, exactly same here, because I have uncertainty here, so I am going to shift uncertainty on the higher order discontinuous term, and finally this is converted into differential inclusion. Okay. So g I have defined here, and g dot I have maintained like this. So all uncertainty is going to transfer here. So differential inclusion formulation comes on the higher order derivative. Okay. So using Filipov regularization, I can able to talk about existence and uniqueness of the solution. Now if you see the Lyapunov function, you can see here that this Lyapunov function is continuous everywhere, but not differentiable, because here I am going to use mod of s. Okay. So mod of s is not differentiable at s equal to 0, and due to that reason, whenever I am going to construct v dot, it means that our analysis is not valid on this set. Now what we have to show, since our derivative analysis is not valid on this set, so we have to show that on this set trajectory is never going to stay. So if trajectory is never going to stay, it means that automatically again this case comes into picture. Okay. So in this way one can easily able to prove whenever they are constructing some kind of Lyapunov function that is not differentiable. So obviously v omega is not Lifshitz on this particular set where s equal to 0, and w equal to 0 is also not the equilibrium point, because you can see carefully that here whatever dynamics I have considered, so zeta dot is going to contain some kind of uncertainty. So once s equal to 0, so equilibrium point is not equal to 0. Okay. So since this is not equilibrium point, and due to that reason it is possible to show that even if s equal to 0, trajectory is not going to maintain at zeta equal to 0. So now if you take the derivative, so this kind of job you have to do by yourself, okay, just for the clarity, such that clarity of calculation I have written everything, but this kind of calculation you have to do by pen and paper, then only you can easily able to understand each and every step, and after that I have to apply the Cauchy-Schwarz inequality. Okay, so please do each and every step one by one, and after that you can define one vector like this, and using this vector now you can see that nice matrix comes into picture. So these two matrix comes into picture. Okay, so now our goal is very simple, because this term is always positive. So just I have to show that this matrix P and P bar both are positive symmetric definite. So by doing that it is possible to get the condition on gain. Okay, and due to that reason, if this gain condition is satisfied, then obviously I can able to maintain the phi 1 and phi 2 both equal to 0 in finite time. If you see gain condition carefully, then delta 2 only comes into picture. It means that derivative of rho dot is only involved, rho bond of rho is not involved whenever you are going to decide the control action. Okay, and in this way finally what I have done, I have utilized the Rayleigh inequality, and using Rayleigh inequality finally I have converted whole equation like this. Okay, now I have two system. I have already told you that actually whenever initial condition on S bar is not differentiable, so I have to show that this on this particular set trajectory is not going to remain there. Okay, and it is possible to show by construction of this differential inclusion. So S bar I have removed. So in this way I can able to talk about existence and uniqueness of the solution, and how to define the field Fs you can able to define where uncertainty is also there, and due to that reason I cannot able to maintain along this particular set. Okay, and due to that reason it is possible to show, since this is not the equilibrium point, so finally trajectory is going to leave this set. So only one possibility S and this xi equal to 0, then only we can able to preserve the structure. Okay, now solution property, obviously this is actually omega equal to 0, then some time t equal to 0, one can able to extend this solution. It is possible to show using some kind of inequality that is called Bihari inequality. So using that particular inequality one can able to show that whenever I have this kind of differential inequality, then that is finite time stable. Okay, so Bihari inequality I am not going to state here, but if you have interest then please go and explore this. Now one very important theorem play a role here. Since I have some kind of Lyapunov function that is continuous but not differentiable, so now if just I will show that V dot is hold almost everywhere and VW is continuously decreasing, then it is possible to show that largest invariant set is 0 0. Okay, so same kind of things one can able to establish using this particular inequality, and then one can able to calculate the finite time. Okay, so those who has interest in multi-agent formulation or multi-input multi-output super testing, you can able to visit one paper that is published in ISA Transaction, and title of paper is Robust Continuous Finite Time Controller. Okay, for multi-input multi-output systems. Now once omega equal to 0 after finite time, then only I have one choice, that whole dynamics is represented by this, because this continuous part phi dot equal to u0 once s equal to 0. Okay, so now whole dynamics is governed by somehow this control action. So again I have to prove that phi 1 and phi 2 equal to 0. So this control I have constructed such that homogeneity is maintained. Okay, if you check carefully, then homogeneity is always maintained. So V dot if you construct V like this, and after that V dot if you calculate, then it is possible to show that this is positive semi definite. Okay, but degree of homogeneity is actually negative, and this is positive semi definite, and phi equal to 0, actually V equal to 0, but phi equal to 0 and phi 1 not equal to 0, that is not going to maintain, because if you substitute phi equal to 0, then finally trajectory will leave that set, And in this way, using Lascelles invariance principle, it is possible to show that if phi 2 equal to 0, then only one possibility I have, that is phi 1 equal to 0. So how basically people are proving phi 2 equal to 0 from here, and after that you can substitute phi 2 dot equal to 0, and maintaining this you can see that phi 1 only equal to 0, that is the choice. So in this way you can able to apply the Lascelles invariance principle, and finally using Lascelles invariance principle you can able to establish that phi 1 and phi 2 both are the asymptotically stable. And after that, by property of the homogeneity, you can see that degree of homogeneity of whole differential inclusion, multi input multi output differential inclusion is -1, and due to that reason, due to negative homogeneity and asymptotic stability, I can able to talk about the finite time stability. Okay, and due to that reason phi equal to 0 in finite time. So that kind of conclusion. Once phi 1 and phi 2 equal to 0, then it is possible to show that error dynamics is going to converge like this. Okay, now once I have this dynamics, from this dynamics I have to prove that this somehow going to converge to x10. So how to prove that? So since I know that whatever L matrix has construction like this, and one of the eigenvalue, exactly one of the eigenvalue is exactly 0. So corresponding eigenvector is 1, and after that I can easily able to incorporate that term here, and in this way I can able to show this. Similarly, I can able to show that velocity is going to converge to finally this point. Okay, easily you can able to do this, and whenever formation comes into picture, so again L bar plus B bar is invertible, means this matrix is invertible. So you can easily able to prove the formation also. Okay, formation with respect to some kind of constant formation with respect to the leader you can able to achieve. Okay, and in this way I can able to get complete formation, means all position vector is going to converge here, velocity will converge here, and I can able to maintain the directed spanning tree. And what I have done during simulation, I have taken 4 agent, and after that x1 equal to 0 and x2 equal to 0 0 I have taken. Initially I am assuming there is no control to the leader. It means that leader is actually moving with some kind of whatever position they have, they are going to maintain, and after that I am going to maintain 0 distance formation, and for formation I have taken 4 agent, and due to that reason all are in different position. I have taken this set of gain. Okay, and these are the initial condition, and these are the set of the disturbance I am assume, and after that you can see that for 0 distance formation, so all agent is going to actually, since the control to the leader is 0 due to that reason, and if initial condition equal to 0, so what leader is going to do, or initial velocity they have, so they are going to maintain their initial velocity 20, and due to that reason all follower is going to converge to 20. Okay, so this is nothing but consensus problem, and that is also called 0 distance formation problem. So this is the error estimation, and this is the control. So if you see control carefully, then control is continuous. Okay, and after that formation also we have maintained with respect to 20, because I am giving u equal to 0. So by Newton's first law, means their position is not going to change. In this way I can able to maintain the space formation. This is the error of the estimation, and finally control, easily you can see that control is again continuous. Okay, so what is the conclusion? First we have understood how to formulate the multi-agent problem, and after that we have designed some kind of continuous finite time controller. So in this way you can able to understand how to design continuous super twisting, higher order super twisting for multi-input multi-output system, because so far whatever higher order sliding mode control I have discussed, most of them that is only applicable for single input single output system, but using this methodology you can also able to apply higher order sliding mode control for multi input multi output system, and there are several systems that is actually represented by multi input multi output form, and due to that reason I have included this particular lecture in this particular course. So with this remark I am going to end this lecture. Thank you very much.